All right, we're going to get the basics of calculus now, the derivative and the integral, but we're not going to be able to go in depth in it as we need to. This is just the quick basics of what we need to use in AP Physics, or at least I should say the first step in what we need to use. There's a lot more, and please remember there's an entire class or multiple classes in college dedicated, in fact tons and tons of classes dedicated to this. So this is just the basic idea. Now, calculus, the derivative part, is all about, really all of calculus, is all about rate of change, which is kind of what physics is about too, rate of change, how quickly something is changing. For example, here is a position time graph. So we're looking at displacement and time, and if you remember correctly, the slope of a position time graph, right? Change in x over change in t, well that's the velocity. Slope is the velocity. And that's nice and easy whenever you have a straight line, because we all know how to get the slope of a line. But what happens whenever it's not a line, whenever it's a curve? Like this would be an acceleration curve here, for example. So what do you do whenever you need the velocity, the instantaneous velocity at 5 seconds? Because all you know is the position at 5 seconds, right, where it's at on the position time graph, and you know that just because of the graph, this is an acceleration one, so the velocity is constantly changing. How do you get the slope at that point? Well, now technically we would draw a line tangential to that point, but I'm getting ahead of myself. You could approximate it. So here's what I mean. What if we took 2 points around 5, let's say here and here, equal distance from 5, and I don't think I got that equal distance, but that's okay, at 4.5 and 5.5. Well, now I've got 2 points make up a line, so I can try to draw my line in there, and I find the slope of that line, and that's a okay approximation for the slope at 5, right? Because now I have 2 points, I can plug into change in y over change in x up here, right, and find the slope. But it would be even better if we drew these points closer together. So let's do that. Let's bring the points even closer together. Let me see if I can't change my colors here, and I'm going to stop actually trying to label what these points are number-wise, because I'm not going to be able to do that. So now whenever I draw this line in, the slope is going to change just slightly, and you notice it's even better, right? Now imagine drawing it in again and again and again. If I call this area here between delta t, or the change in time between, or the distance, the change in the time between the 2 points that I'm choosing, and so here's my delta t, right, for those 2 points, you can say, hey, if we can get delta t, the distance between the 2 points, around the spot I'm trying to get the slope of, thinner and thinner and thinner and thinner, eventually we will get such a good approximation, we can call this, yes, this is the slope at t equals 5. So whenever delta t equaled 0, so now as they scrunch inwards, if you will, as this one comes in and as that one comes in, and they finally actually meet literally at 5, that's going to be the slope at that point. That's actually called the limit. Now here's the equation for the limit, and it's pretty simple. Limit is delta t equals 0 of, remember, x of t, this is the function x according to time, so x of t, this would be the second point of whatever your t was, right? Your initial t plus delta t, so the 5.5, minus x of t, right? So that initial, all divided by delta t. Well, that's going to give you that point there. This is just the slope formula as limit goes to 0. Now, that might seem confusing, but whenever you do that, you'll eventually get, bringing these points closer and closer in, you'll actually get the instantaneous velocity by the tangent line. And a tangent line is a line that only touches the graph at one point. So the slope at any one point is the tangent line to the curve. Now you might be saying to yourself, Mr. Perch, you want me to either get closer and closer and closer, calculating the slope over and over and over again to see what it eventually starts to get to. For example, if you were thinking just number line here, if we started at 10 and then I said 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.5, 0.2, 0.1, 0.07, 0.03, 0.01, 0.001, 0.0001. You would eventually go, if I keep going down and down and down, you realize he's not passing 0 but he's getting closer and closer to it. That's the limit. The limit must be 0. But you want me to do that with a slope, getting closer and closer and closer, and figure out what the slope is? Well, that's kind of crazy. Or you want me to actually go through this mathematical idea of the limit, and I'm not even sure if I've been taught that in my math class, or if I have, it's not something I exactly want to do. Well, the answer is no. I don't want you to do that. Instead, I want you to use something called the derivative. The limit idea is the definition, if you will, of the derivative. It's how it came about. Now, the derivative is actually very simple, and we're just going to deal with power rule. What power rule says, and I'm going to use, let me point out the definition over here. D means change in, same as the triangle. So change in this function, right, x, is the variable to the n power, n is a constant, according to, down here, the change in x. So according to x. This tells us what variable we're going to take the derivative according to. So in other words, n is our constant, x is the variable we're actually going to take the derivative to. So now check out my 5 examples that I'm going to do for you here. By the way, it does show you what we're going to actually do. You take whatever's in the exponent, whatever constant's in the exponent. This is assuming here's your variable, you have a constant in the exponent. You bring it down out in front as a coefficient, and then you subtract 1 from the constant in the exponent. So now I'm going to take the derivative, number 1 here, of t to the 3rd power according to t. So t is my variable. So I bring the 3 down. I got 3t, all right, the variable still remains. And then up in the exponent, 3 minus 1 is 2. Nice and simple. No need for limits. And that is the derivative of that function. Now, this is, whenever you take the derivative, you get a brand new function. That function is the function of the slope. That's the beautiful thing of it. So if I wanted to know what is the slope at t from this equation, t to the 3rd power, right? If I want to know what is the slope at 2 seconds, what you can do is you can take the derivative of the function t to the 3rd power. You get this equation over here, right? This is now the equation that'll tell us the slope, and so you plug 2 seconds in for t, and boom, you got the slope at 2 seconds. Nice and easy. Number 2, you'll sometimes see the function actually written into part of the derivative. In fact, lots of times this is more proper whenever you actually write it up here in the numerator. Change in the function according to time, but you won't see it happen all the time because eventually these things get so long that we like to abbreviate and then put brackets around because this is the same thing, right? You can multiply that into the numerator. So whenever I do this, 3t, right? That's to the 1st power. 1 times 3 is 3. And 1 minus 1 is 0, and anything to the 0 power is 1, so the t just completely goes away. Minus, now I'm going to multiply this 2 down. 2 times 4 is 8, and then 2 minus 1 is 1, right? T to the 1st power is just t. Let me go back and point out something here. T, right? Whenever this has an imaginary 1, 1 times 3 is 3, and this imaginary 1 minus 1 is 0, right? So t to the 0 is 1. That's why that t disappeared. Just want to go back and re-emphasize that. Anytime, number 3, you take a derivative of a constant, there's nothing there. Derivative of a constant is 0. I mean, just imagine graphically a flat line. What is the slope of a flat line at x equals 4? Well, the slope is always 0. 4t, right? This is the exact thing as we already did in number 2. That's just going to be 4 because t to the 1st comes down. Now here's a bunch of things together. That's not a problem. You do each one individually. Let me back up and say that. If there's just additions and subtraction signs between them, you can use the power rule on each of the terms in the function individually. So on the term 2 to the t squared, I multiply the 2 down. 2 times 2 is 4. And now I subtract 1 from the 2 in the exponent. 2 minus 1 is 2, so I just have t. Plus, now, leave the sign in between the same, 7t to the 1st power, right? So multiply the 1 down. 7 times 1 is 7. And then t to the 1st minus 1, that's t to the 0, so it just goes away, right? 4t plus 7, and then I have a constant, right? Minus 5. Derivative of a constant, we already learned in number 3, is 0. So the answer would be 4t plus 7. I hope this is making a lot of sense for you. Using this rule, you just multiply down the constant and subtract 1, right? Pretty simple for the power rule for derivatives. You do each term separately, like down here. A couple of reminders. If you have a position time function or a position time graph, kind of like this and this graph up here, right? The slope is the velocity. That means if you take the derivative of a position time function, you get a velocity function. Same thing here with a velocity time function or a velocity time graph. If you take the derivative, right, slope, you get the acceleration. So look at this equation. Here's one of our kinematics. Now imagine x naught is 0 and v naught is 0, right? And a was gravity, right? That means 9.81. We're just going to use 9.8 there. That gives us a function xt of 4.9 t squared. Whenever I take the derivative of that, so if I do d dt, so I'm taking the derivative according to time. If I put d dx, right, where the x was in the denominator according to x, there is no x there, so all this would just go to 0. It would be treated all as a constant. But never mind all that. If I take the derivative of this entire function, that would leave for me vt, the velocity function, equals, multiply the 2 down, 9.8 t, and now up in the exponent 2 minus 1 is 1, so 9.8 t would be the velocity function. And then I can plug in any time I want, 1 second, 2 seconds, 3 seconds, into this t and figure out what the velocity is at that point. So even though the function is changing, right, I can figure out the velocity at any point here. This is also another way you could attack your kinematic equations, right? Those problems, because there are kinematic equations for everything. But you could technically just write one equation, like this one here, that doesn't have final velocity in it, but then say, not a big deal, I'll take the derivative of it, and now I've got final velocity in it. You know, and then v naught was 0, but let me just kind of point this out. If it wasn't 0, if it was something else and you took the derivative of it, it would just have what that plus v naught is. That t would go away. You'll see that in the next slide. All right, so here I have one of our kinematic equations, and I'm going to take the derivative of it, and I want you to see what happens. So as you can see, whenever I take the derivative of that, derivative of constant 0, derivative of some constant out in front, I don't even have numbers, I can still deal with that. So derivative of some constant out in front of the variable I'm dealing with, t, right? Multiply the 1 down, 1 times v naught's v naught, and the exponent 1 minus 1 is 0, so the t goes away. Multiply the 2 down in this one, 1/2 times 2 is 1, so that becomes a 1 in front. 2 minus 1 is 1. A is a constant, so that stays right there. So it's 2 times 1/2 a, right, and the 1/2 and the 2, they get canceled out because 2 times 1/2 is 1. I end up with, hey, check that out, that's another one of our kinematic equations right there. And if I take the derivative of this, I'm going to end up, derivative of velocity is acceleration. Let's actually put in the proper d dt in front of it of this, of this function. Technically, I should have put this up here in brackets as well. Derivative of constant v naught is 0, derivative at, well that's just a, which gets us to, hey, if this is a constant velocity one, a constant acceleration, which all of our kinematic equations are set up for, eventually a is just a, it's just a constant acceleration. But I want you to see how taking the derivative just leads to a different one of our kinematic equations. All right, so a couple of example problems. I've got a function, x of t, so position according to time equals at squared plus bt plus c, where a, b, and c are just constants, and t is my variable as indicated by the x of t here. So given that function, number one, please find velocity and acceleration functions for that. So in other words, I have a position function. Let's take the derivative of it. Now, I'm not going to notate this correctly for the sake of time, but velocity, according to time, taking the derivative of this, this first part here, multiply the 2 down, so I end up with 2a t, right, because 2 minus 1 is 1, so that's 1 up there, plus b, right, and then there was imaginary 1 and that t there, so 1 minus 1 is 0, plus c, and the derivative of a constant is 0. Now whenever I go for my acceleration here, take the derivative of this, and I guess I'll give us some notation, d dt, so take the derivative according to time. I should say that for the derivative of a position time graph according to time is the velocity, and the position and the derivative of a velocity time graph according to time is the acceleration. That part's critical. It's rate of change according to time. So here, whenever I take the derivative of this just becomes 2a, right, is going to be whatever the acceleration is. Now, part 2 down here gives us some numbers. A equals negative 4.9, b is 25, and c is 50. So in other words, if you're thinking about this in terms of a kinematic equation, right, here's the initial velocity, that's the initial velocity spot, right? Here's the initial position, x naught, that's the initial position spot. So what if these terms were mixed up? It used to be in our kinematic equation CBA, right? And this entire term was at the end, and this entire term was at the beginning. So what? Not a big deal. Now I'm asked to find the object's velocity and acceleration at t equals 4.5 seconds. So let's come over here to my velocity equation. V of t equals 2 times negative 4.9 times my t of 4.5 plus b, and our b is 25. And I end up with a velocity of negative 19.1 meters per second. Using significant figures, that has to become negative 19 meters per second. And now for the acceleration, well, that's pretty easy also, right? That's just 2 times a, which is negative 4.9. So that gives me an acceleration here of negative 9.8 meters per second squared. All right, let's see if we can rapidly talk about the integral. Now, the integral is the opposite, if you will, of the derivative. Specifically, it gives you the area under the curve. It goes backwards, if you will. Now, you've already been taught that to find the area under the curve of a velocity time graph, what you can do is you can divide it off into pieces. Like for this graph, you could divide it off into a kind of a rectangle and a triangle, and you can find that the area of a rectangle and triangle very easily. And you also have already been taught that the area under a velocity time graph is the position, or excuse me, the displacement, the change in position, and the area under a acceleration time graph is the change in velocity. But what happens whenever you get a graph or object or function that looks like this? So here's this function according to velocity. This does not have a constant acceleration. This has a changing acceleration on us. So what do we do now? Well, once again, to find the area underneath, you're going to have to take the integral. The foundation behind that is this. Imagine drawing in little rectangles, tons and tons and tons of little rectangles. Now I went ahead and drew those in for us. Whenever you do that, now you can find the area of a rectangle, right? You do the base down here times the height of it, which you could find at that point, right? Because you have a definite spot down here that you're going at, and you have a then you could plug into the equation whatever the time is and figure out at what height that rectangle is at. Now, notice that you have a little bit of space missing here, but the more you fit in, right, the more you can fit, more of these rectangles you fit in, the smaller you draw them, or the smaller delta t is, in other words, the width of these rectangles, the more rectangles you fit in, and the less little space you have missing up here at the top. So what we could do, and by the way, you'd have to add up all of the areas of these rectangles. Mathematically, what you could do is you could sum up the rectangles. This means sum of from wherever you want to start, point A, to wherever you want to stop, point B, and getting the area underneath. And you could stop anywhere in here, point B, or start anywhere in here, point A. Generally, though, you know, the entire graph is what's used. You'll see in physics, though, that we'll start and stop at whatever times we want. Here's the height, the function, right? The y, you plug in a time into the function, you get some y value, times delta t, that's the base of the triangle. So this is the area of one triangle, so I'm adding up all the different triangles, but I'm going to set the limit as delta t goes to 0. Start shrinking these in to where you get more and more and more rectangles. That would get you the area underneath. Sounds somewhat complicated. It's not very bad. They're going to go over how to do that in calculus. Instead, I'm going to teach you the integral. The integral, this right here is the equation that is the foundation of the integral. But the integral is the opposite of the derivative. It gets the area under. The rule is this. If you have, power rule, if you have some variable x, and we're going to take the integral according to dx, so notice dx used to be in the denominator, or dt used to be in the denominator of the derivative. It's multiplied to the other side now. X to the n dx, right, this is the integral sign here. What you do is you have to add 1. The derivative, you subtracted 1. This is the opposite. We're going, if you will, up in power. So you add 1 in plus 1, but you have to make it where it can be undone. So then 1 divided by whatever this new number is, plus c. We'll talk about that plus c here in a minute. A good way to make sure you're doing the integral right is simply after you get your final answer, take the derivative of it and make sure you get back to whatever you had. So let me do number one here for us. I've got x to the third, right, because of the plus 1 part here. So 2 plus 1 is 3. And then, now the next part, 1 divided by n plus 1. So 1 divided by whatever is up here. Now that's 1 over 3. If I took the derivative of that, right, it would get me back to x squared, because it would be 3 minus 1 is 2, right? And I would take whatever the 3 was and multiply it down, and 3 over 3 is 1, so it would get me back exactly where I need to go. If you need to pause the video to think about that right now, this would be a good time to do it. Moving on to number 2, I'm going to add 1 up here, right? So now I'm up to x to the 5th, and I'm going to take this 5 and multiply it down in the denominator, so 3 fifths. Now, once again with number 3, just like with derivatives, you do each term inside of a function separately. So negative 4.9 t, and now t squared, right, because it used to have a imaginary 1 there, 1 plus 1 is 2, divided by 2. Now, negative 4.9 divided by 2 is not proper whenever we're talking about fractions here, but your calculator doesn't care. Just make sure you're not reporting answers like that, because it would be marked wrong every single time. Plus, now this 20 doesn't have a t after it all. If anything, you could imagine it having a t to the 0 power. So this now becomes t to the first power, right? 20 times t to the first power. And that means I need to divide the 20 by 1, move the 1 down to the denominator, so that's not a big deal. So the answer here, negative 4.9 over 2, t squared, not proper, but that's okay, plus 20t. Don't worry about this problem down here just yet. We're going to do that in a couple of slides. And by the way, I made a very, very large mistake. I didn't put on plus c to all these. Plus a constant. You always must put on plus a constant there. These constants are going to stand for the initial position or initial velocity as we get going. Please make sure to write plus c in. And if you're given what the initial position or velocity is, make sure to put that on. So please do not forget the plus c. So what's up with this plus c idea? Well, let me see if I can't briefly describe it. So here's a velocity time graph, and I could get the area under if I knew the function by taking the integral, or it's a rectangle, so that'd be nice and easy. And I find, let's just make something up, that the area underneath here, the change in position, delta x, should be, what do we have, 5 and 4 over here, so delta x should be 20 meters. But then whenever I come down here to this bottom graph, x and t, where do I actually start from for this velocity? I mean, technically, if I started from 0, right, I could make this, have a slope of 4 and go up like this for 5 seconds, and this would have an area, right, or a change in displacement all the way up here, up to 20 meters. But it would be just as equally right if I started from some different x naught and I went up here. And so if this, let's say this started from 5, now this is going to come over here to 25, right? And the area that I covered, the change in displacement, still is going to be, excuse me, not the area under, but the change in displacement still is 25. So that's the idea with plus c. It doesn't tell you, this kind of graph and taking the integral, finding the area under, doesn't tell you the correct starting point. That's the plus c. Where is the starting point? Because technically it could be anywhere. So that's why it's so important to get the plus c on there. And lots of times you'll actually write in v naught or x naught. You'll see that as we continue to go with class. Now, I'm going to go ahead and do the reverse of what I did earlier here, taking a constant acceleration time. If I take the integral, right, of this according of at, which is a, according to dt, the integral of this is going to get me the integral of acceleration going backwards is velocity, right, which is going to give me at plus c. And you can probably guess what that plus c is this time. It's a velocity, so that's going to be the initial velocity equals at plus v naught. Hey, that's our one of our kinematic equations, right? Just the v naught and the at are switched in place. Not a big deal. Now, if I took the integral of this entire function according to dt, right? Pardon the not exact proper notation here. But if I took the integral of that according to dt, the integral of velocity is position. Now, there's an imaginary 1 right here, right? There was an imaginary, by the way, t to the 0 there. That's how the t came about. So there's imaginary 1 up here now, so I'm going to end up with at squared. And I have to make sure that squared part can get undone. It has to go down the denominator here, right? 1/2. The same thing happened right here, 1 over 1. This 1 came down into the denominator. 1 over 1 is 1, so that's why it didn't matter. So 1/2 at plus, now there's an imaginary t to the 0 here, right? So this becomes v naught t plus c. And you can imagine what that c is going to be, right? This becomes 1/2 at squared plus v naught t plus that c is my initial position, one of our other kinematic equations. One last problem, this video has been insanely long. The graph of the motion above with this function vt equals negative 3t squared plus 27, so we don't have constant acceleration, it's changing, describes a guy hitting the brakes to try to avoid running a red light 50 meters away, and he's actually pushing the brakes harder and harder and harder and harder. That's why his acceleration's going up. He's realizing, oh crap, I'm about to run this red light. So he's trying to avoid that, and the question is, was the driver successful? Well, I have a velocity time graph, but I need to know, did he actually go into the intersection? What was his final position? So what I can do is I can take this velocity time and I can actually take the integral of it. So I'm going to take the integral of negative 3t squared plus 27. That's the velocity time according to time. So I'm going to take the integral of that, and this is going to give me, let's see here, negative 3 over 2, right? Excuse me, 3 over 3 t cubed, right? Because 2 plus 1 is 2, and I got to bring that 3 down. So negative 3 over 3t cubed plus 27t plus c, right, where c is x naught, and I'm going to assume that x naught here is 0 in this case. All right, so that's what my position x of t graph function is. Now, if we only knew the time that this car stopped, right, whatever time he stopped at, which it didn't tell us in the word part of the problem here, if I knew the time that he stopped, it would be simple. I just plug that time in, right, to those two, and I come up with my answer. But I do know the time that he stopped. Check out the velocity time graph, right, or the velocity time function. Whenever his final velocity is 0, so v of t equals, let's copy that equation back down, plus 27. Whenever his velocity is 0, his final velocity is 0, that's when he stopped. And that will let me solve for the time. So let me go ahead and solve for that. So I come out with, because of his velocity time function, and I set it equals to 0 to figure out when he stopped, because when your velocity is 0, he stopped, I came out with 3 seconds, which now I can plug up into this equation, the position time equation that I got from taking the integral, right, to find out how far he went in those 3 seconds. I end up finding out that he went 54.0 meters, so that means he did run the red light. He did slide out into the intersection and started to go through it. So he's out in the middle of the intersection right now. He did run this red light. A few things to point out here. 3 divided by 3 is 1, and so the negative 1. Another thing for you. This cubed here is on the t, 3 cubed with the negative out in front, not negative 3 cubed. Okay, so be careful what you do first, your order of operations with these parentheses here, because the negative wasn't already part of the t. It wasn't a negative time. That doesn't exist. Also, the time here, whenever you take the square root, technically you have a plus or minus. So technically this is plus or minus 3 here, but I think it's fairly obvious. We don't have negative time. We don't go backwards in time. So it's a positive time that I plug back in. All right, I hope that helped you understand the basics of calculus, and I will see you in class.